Hello, everyone. This is meteorologist and storm chaser Gabe Garfield, and I'm going to be presenting on basic meteorology for storm chasers. This is the same presentation I gave to the National Storm Chasers Summit in Fort Worth, Texas in February 2024. What's ahead? First, I'll cover an introduction of how we're going to approach this material. Also, by the way, there's going to be a second video that will get into some more advanced topics, so this approach will apply to that one as well. And we'll dig into the weather charts, upper air, surface, Skew-T Log-p, and Hodograph. So before that, a little bit about me. I'm from Oklahoma, and when I was a young boy, I had my first encounter with a tornado in Stillwater, Oklahoma, and that fascinated me. And I was definitely a Twister generation guy. I also watched that movie so many times and got very interested in severe weather and tornadoes. And ultimately, that landed me at the University of Oklahoma, where I got 2 degrees in meteorology. And my master's thesis was focused on maximum wind speeds and tornadoes. It was just an amazing experience. Also, during that time, I got to participate in Vortex 2. I was a navigator for Mobile Mesonet Probe 4, which was basically a soccer mom van outfitted with weather sensors. We had an amazing time, though. Did some great science there. Also, during that time period, I had an opportunity to chase with the Doppler on wheels and accidentally, I should say, got roped into storm chasers, working with the tornado intercept vehicle. I didn't intend on that, but it worked out that way, and it was a great experience. Got really close to several tornadoes, and it was definitely an enjoyable time. And after that, I got involved at the National Weather Service in Norman, Oklahoma as a weather researcher. Did that for 8 years. And all this time, since the year 2000, I've chased tornadoes in the plains. So it's been almost 25 years. It's just been an incredible experience for me. A few of the tornadoes I've seen some pretty nice tornadoes in terms of shapes and photogenic quality. Also, some mean ones like Hallam in 2004, which was the world's largest tornado for a number of years until El Reno, I believe, in 2013. Moore, Oklahoma, big F5 there in 2013. This was definitely not one of the more fun ones that I've chased. It was just a very destructive, very sad situation. So most of them, fortunately, are not like that, but that particular one was not very fun to chase. I also got to chase this rather photogenic wedge tornado in May of 2016 near Sulphur, Oklahoma. So with that, let's get right into the introduction. So supercell thunderstorms. We're going to start with this because this is a good place to begin. Supercell thunderstorms are responsible for 70% of tornadoes. So let's get into some facts about supercells. They are rotating thunderstorms by definition. So that means their updraft spins, and that spin actually keeps the downdraft or the rainy part of this thunderstorm from interfering with the part that goes up. So that means that these storms can last for a very long time, greater than 7 hours. And in some cases, like in 2006, it can last for more than 12 hours. There was a supercell that formed in northeastern Oklahoma and moved all the way up into Michigan. Just unbelievable how long some of these supercells can last. These supercell thunderstorms produce almost all of your EF4, EF5 type of tornadoes. So this would be your Joplin, Missouri type tornado, Tuscaloosa, Moore, Xenia. Those type of events are produced by supercells. And also, they produce almost all giant hail, which is greater than 4 inches in diameter by definition. So the reason that we cover supercells, not only because they produce these big events and they're very impressive, but because they also reliably produce tornado ingredients. Now, it doesn't mean that every supercell is going to produce a tornado, but if you're going to have a tornado, more than likely it's going to be produced by a supercell. So if you can forecast supercells well, you increase your chances of finding tornadoes. So for supercells, you need instability, moisture, vertical wind shear, and lift. Now we'll cover each of these topics in detail in the second video, but first we'll need to cover how to read weather charts. So let's start with the surface map. So if you're looking at this for the first time, you may have no idea what this means, other than that you could see the state of Texas, Oklahoma, Kansas, Nebraska. You might be able to identify that, but you would have no idea what these little barbs and flags are all about, and the circles and the different symbols and so forth. You'd see some numbers. You might think that maybe that has something to do with temperature, but you would have very little idea of what's going on here. By the way, this map is from one of the more infamous outbreaks of tornadoes in Southern Plains history, May 24th, 2011. Look it up. It was a very impressive day. There were three violent tornadoes officially in central Oklahoma that day. Two F4s and one F5. Arguably, they were all F5s. Just an incredible event, and one that I actually chased. I got to see two of those, and it was just a very, very incredible day. But you wouldn't know how to read this map if you didn't know how to read a surface chart. So that's next. The station plots are those little, those little locations on the map where you see the circles and the wind barbs. So we'll talk about that in detail here and explain what each of those pieces actually means. So to begin, the wind. So this is basically a long flag with some barbs at the end of it. It's pointing, if you were thinking of this almost in polar coordinate sense, it's pointing from the northwest to the southeast. So it is actually a northwesterly wind, is what you would say. So this is also, by the way, the barbs correspond to the magnitude of the wind. So you see this long barb that corresponds to 10 knots, and that short barb corresponds to 5. Put 10 and 5 together, and that's a 15 knot wind from the northwest. Now, moving counterclockwise, you see this 57. That's just the air temperature at the surface. So that's one of the more easy ones to identify. Then you have this weather symbol here below the temperature. That's 3 dots. I believe that represents, I think, moderate, maybe even heavy rain. Honestly, I've forgotten most of these weather symbols here, but if you're curious about that, look it up on Google. You can find all the information there. Typically, it's not terribly important to know that unless you're trying to find out about snow or something like that, because you can see most of this stuff from radar anyhow. But underneath that, you have the dew point temperature. In this case, is 56. So this is interesting because it looks like the temperature here is 57, the dew point is 56. In meteorological jargon, you might say that's 57 over 56. 57 meaning the temperature, 56 meaning the dew point. So anytime you hear something over something else, it's temperature over dew point. Sky cover, in this case, is clear because the circle is white. If that were filled in with black, that would be, overcast. These are kind of filled to the extent that the sky is covered with clouds. So if you have 1/4 of this covered in black, that would be partly cloudy. And then you have the pressure trend in millibars. In this case, the pressure was dropping at 6 millibars over a period of time. And you have the sea level pressure here. We won't go too much into detail on the pressure, but you get the idea. Now, in terms of the wind barbs, this is just to show you how to represent the wind speed. In particular, the wind direction, except in the case of the calm, is actually from the northeast. So you see this flag is pointing to the southwest. So calm here, you've got a circle with a little dot in the middle, and then the little kind of broken looking wind barb here, that's 5 knots, and then you've got 10 knots and 15 knots and so on. So basically the number of barbs corresponds to the wind speed in knots. So 10 knots times whatever number of barbs you have. So that is true all the way up into 50 knots. And there you get a flag. And then the flag, you add some more barbs and so on. So you get kind of the pattern here. The barbs equal 10 knots, or half a barb equals 5 knots, and the flags equal 50. And by the way, these winds around here, so you know, above say 100 knots, you typically don't see those very often, except at the highest levels of the troposphere, which is where all of our weather happens, by the way. So hand analysis. So the same weather chart, or I guess the surface map here from May 24th, 2011. Let's throw in some hand analysis. So this is what is known as the 70-degree isodrosotherm, which is just a fancy way of saying a line of constant dew point. So what that means is you'll notice that here in central Oklahoma, let me just point out this station right here has a 72-degree dew point. You see that kind of in the greenish color there. And so basically to the right of this line that I drew in, you have dew points in the lower 70s. And to the left of that, you have dew points that are less than 70. So you draw the line right in between. And the reason you do this is it actually helps to visualize or illuminate what's actually going on with the weather there. So this is known as isoplething. So basically taking any quantity, temperature, dew point, whatever, wind, speed, and getting a good sense of it by plotting it. And here in this case, I've plotted the dry line. This is just showing roughly the difference between the boundary between the warm, moist air over Oklahoma and Kansas and the dry desert Southwest air just west of the dry line. So you can see here in central Oklahoma, the winds are kind of from the southeast and southeasterly winds, and this is a pretty common pattern for severe weather. And then out to the west of the dry line, the winds are coming from the southwest. Obviously, the dew point drops a little bit. Actually, if you look out in West Texas, dew point of 17, very low. So that firms it up. And the dry line, by the way, is a very strong focus for the development of supercells during the spring. And then the warm front, this is somewhat subjectively annotated here, but basically it shows the difference between relatively warm temperatures to the south and relatively cool temperatures to the north. You'll see that it's a little bit fuzzy where that is. Just generally shows about 80 degrees as the location of the warm front. But that is, again, fairly up to personal interpretation. But warm fronts are moving in the direction of the cool air. So in this case, cool air is off to the north. So the warm front is moving off to the north. And then the opposite is true for cold fronts. Those are bringing cooler air into the warmer air. So in this case, the warmer air is behind the dry line. So the cold front is coming from north to south. And then the center of the low pressure is actually right there where those intersecting lines occur. This is known as the triple point. That's where the cold front, the warm front, and the dry line come together. So three things, the triple point. And that's where a lot of storm chasers will actually focus on their targets right here, just to the northeast of the sort of bowing out dry line, the bulging dry line. In this case, of course, if you did, if you did actually target that area, you would have been a little disappointed. It turned out most of the severe weather, as I mentioned before, the big nasty storms happened in central Oklahoma. But you can see there's a good reason for that. The moisture here, the 72-degree dew points, a lot higher than what you see here in southern Kansas, 61. So you could have inferred that central Oklahoma was a better place to be. So how to read an upper air map. This is the same day, May 24th, 2011, 7 p.m. So, a lot of storm chasers know what this looks like, negative tilt trough. I won't get into exactly what that is, but basically, if you see something that looks like this out there in the 500 millibar chart, so which is, say 15 or 20,000 feet above the ground level, this is spelling trouble for whatever area is just east of that. So just to orient you here, those black lines, you see these dark black lines right here, those are representing constant height above ground. So in this case, we're talking about a 500 millibar chart, which 500 millibars represents a pressure surface. So the height above ground where it is 500 millibars is this line right here. And it actually has a number associated with it. I believe this one looks like it's roughly about 584, maybe a little bit lower. So that's roughly 5.8 kilometers above the surface is where 500 millibars is. And as you go north, these lines, those numbers, those purple numbers get a little bit lower. So that means the 500 millibar surface is lower here. So there's actually turns out lower pressure as you go north in this case. By the way, height and pressure are essentially, you can swap them out. They're essentially two sides of the same coin. This is derived from something that's called the hypsometric equation. I want to get into the details on that, but basically, when you see height, think pressure, and when you see pressure, think height. So it's pretty much synonymous. And then the temperature lines here are dotted. You can see these all over the map here. You notice that as you get closer to this guy right here, which is little kind of peanut shaped area over Wyoming and eastern Colorado and western Kansas, that is the center of the low pressure or the uh, lowest heights on this 500 millibar chart. You'll notice that the temperature lines are actually pretty nicely co-located. It turns out there is a relationship, I won't get into it again, in the atmosphere where basically if your temperature lines are really, really close together, you're going to actually have pretty strong winds. And you can see here that you do have a flag and a couple of barbs there. So the wind is stronger where you do see that tighter temperature gradient is what you call it, when all those temperature lines are kind of packed there nice and tightly. And then, of course, the wind barbs that we've already talked about. So what do you notice about the direction of the flow relative to the isoheights? So again, the isoheights are these black lines right here. You notice about the direction of the flow relative to that. Well, the wind is flowing parallel, and that is not an accident. And that brings us to our next topic. But first, we're going to talk about two rules about pressure. And rule number one is air flows from high to low pressure. So you've got the high on the left and the low on the right, and air flows from high to low. And this just generally means that high pressure means you've got a lot of molecules kind of packed in there nice and tight, and that generally through diffusion, they want to move to where there are fewer molecules because they interact fewer times in this direction. So air flows from high to low. Now, the second rule is wind speed is proportional to the magnitude of the pressure gradient. So, what do we mean by pressure gradient? It just means how pressure is distributed over a fixed distance. So, in this case, case one, you see pressure here, and then you see pressure plus one. So, higher pressure, so the pressure to the right is higher than it is to the left, right? And then compare that to case two. It's the same deal, right? Pressure here, pressure plus one, pressure plus two. Pressure increases as you go to the right. But notice in case two that these lines are a little bit closer together. So first question is, what direction will the wind be facing? Wind will be moving toward rather. And which one is going to have the faster wind speed? Well, it turns out that the wind is going to be pointing to the left, right? From high pressure, P plus 2 to P to the left, high to low pressure. And because the second case has closer spacing of these isobars, you actually have stronger wind speeds here. So that's why we see that. Now, the question is, in that 500 millibar chart, didn't we notice that the winds were parallel to the iso heights or essentially isobars? So why is that the case? That doesn't make any sense since air flows from high to low. Well, the answer is quasi-geostrophic balance. So quasi-geostrophic balance does take into consideration the pressure gradient force, which I've labeled PGF here, and that's air flowing from, again, high to low. But it is actually counterbalanced by the Coriolis force. So the Coriolis force essentially is an apparent force, very much like the feeling of centrifugal force that you feel when you're on a merry-go-round and you feel as you're spinning around like you're moving outward. And the reason that you feel like you're moving outward and there's like a force on you moving outward is because of inertia. Your body is simply an object in motion tends to stay in motion and you're going in the direction that you were previously going just a moment before. Same thing for the Coriolis. And so that always moves to the right of the wind. And so this balances out in the upper part of the atmosphere. Again, this only applies above the friction layer, so this is not something you would expect to see near the surface. This is more like, say, 15, 20,000 feet, 30,000 feet above ground level. So here are the mandatory levels for weather charts. So we have 850 millibars, 700 millibars, 500 millibars, 300 millibars. So these are the levels that when basically National Weather Service offices all across the country are releasing weather balloons, they have to take measurements at these levels. And the reason for that is that you do want to get a nice snapshot of the weather as it's going on across the country all at once so that you don't have time as a variable here that you would want to basically say, in synchronization, this is what the temperature, humidity, wind speed, and direction profile looked like across the country. And it also helps to feed these weather prediction models. So they can use these data as a way to feed their model. Now, moving on to Skew-T Log-p. Skew-T Log-p, or Skew-T as it's known in short, is used to analyze the vertical profile of certain weather variables. These data are collected by weather balloons and include temperature, dew point, and wind. So the constant temperature lines are skewed up and to the right. So that's the Skew-T part of it, skewed up and to the right. And the log P is that pressure decreases logarithmically with height. So Skew-T log P. Now, Skew-T analysis assumes parcel theory. Parcel theory basically says that a parcel is like a bubble of air. So you can think of it, it's a hot air balloon. It's like a bubble of air. And the assumptions in parcel theory is that no heat leaves or enters the parcel. So that's known as the adiabatic assumption. The moisture content stays the same. Everything is self-contained. Like I said, there's no mixing, and rain is not a factor, so there's no drag force. But in reality, we know that dry air can mix out a surface parcel. We see this from time to time out there on the plains where you have really great moisture in the morning, but when the sun comes out, thermals begins to mix the air, and you actually end up with lower surface dew points. That's not the case in parcel theory, but that has to be our assumption. So sometimes CAPE is an overestimate, particularly in situations where you do have drier air above the surface. CAPE, by the way, meaning convective available potential energy, or just a measure of how strong an updraft in a storm might be. Also, rain is a factor in real life, produces a kind of a drag force. So these are not included in parcel theory. So something to keep in mind. So here's what the chart actually looks like. And I'm just kind of zoomed in a little bit. The chart goes above this, but really want to show you the lines because they're kind of tiny. So we wanted to zoom in really well so you can see what's going on here. So the first thing I wanted to point out is this left side, you do see decreasing pressure with height. So as you're going up is higher in the atmosphere. And you can see that the numbers are decreasing on the left. So that's in millibars. So that means that pressure is decreasing. And they get a little bit more spread out as these lines of pressure get a little more spread out as you go up the chart. These are your isotherms in red. So this represents temperature. So again, Skew-T. So these are moving from lower left to upper right. Kind of a weird way to look at temperature, but you get used to it after a little while. Then the dry adiabats here in the blue. So adiabat meaning no heat exchange. So if you move air up the dry adiabat, it will cool at 9.8 Celsius per kilometer. This dry air will do that. Now, if you saturate it, that's a different story. That's known as a moist adiabat, and that rate is a little bit lower than the dry adiabat, so it cools at a slower rate. And that ends up being important, thinking about this in terms of the hot air balloon. So we'll get into this in terms of latent heat release. So this particular image, this particular figure, shows you something very important about severe weather. And let's start by looking at water vapor. So this would be, you can kind of think about it like the air near the surface of the earth, right? Air you can wear on the big severe weather days, very juicy, balmy air. When that moves up in height, right, it gets cooler as you get above the surface, and then the air condenses. So when it condenses, that means it moves from water vapor to liquid water. And as you can see, and if you're moving from vapor to liquid, you're moving essentially from right to left here in this particular image. And that means that heat has been released to the environment, which means that your hot air balloon is warmer than its surroundings. So again, here's the idea. Yeah, warm light air in the hot air balloon. Think just after condensation occurs as you're lifting a parcel of air, and around it you have the environmental air, which is relatively cool and heavy. So what this means is that you have a pressure gradient force, essentially pointing upward, right, high to low. So it's push this cool heavy air is pushing this warm light air upwards. Now gravity is operating in the opposite direction. However, in general, you do have a net upward force, and this is known as buoyancy. So it's just if you've ever heard the term convective available potential energy, this is what that represents. So one thing I wanted to do is put the dry adiabats and the moist adiabats in the same view. Notice how the moist adiabats, once you get to the top part of the chart here, kind of in the upper levels of the troposphere, notice how the moist adiabats align with the dry adiabats there. And the reason is because the moist adiabats will act like dry adiabats when they've released all of the heat energy down here. So basically, down here, that hot air balloon is nice and warm because you're changing phase from water vapor to liquid water. But once you get way up here, you've already removed all that moisture. So you get almost in line, like you can see right here, that the moist adiabat and the dry adiabat are basically on top of each other. So that's something to bear in mind. And then the constant water vapor mixing ratio. So this is basically a way to think about this is essentially dew point temperature. So these are slanted almost in the same direction as the temperature lines. Maybe a little bit. There's a little bit of difference, and I'll explain here in a second what that actually corresponds to and why that's important. But generally speaking, these correspond to surface dew point temperatures. Let me get right into the mixing ratio lines crossing the temperature lines. So you can notice how the red lines here, which are the temperature lines, they slant slightly differently than the water vapor mixing ratio line. So this is how much liquid water there is per unit of dry air, and you can see that this is why a 55 dew point at Rapid City, South Dakota is actually worth more than at Norman. So let me explain in the analysis how this works out. So let's say that Rapid City, South Dakota has a surface pressure of 890 millibars. So it's slightly elevated. It's kind of in the higher planes there. So if it has a 55 dew point, that's 13 Celsius, right? So by the way, that's where Rapid City is, and that's the dew point of 55 plotted on the chart. That water vapor mixing ratio is 12 grams per kilogram, or approximately. Now, if you took that same water vapor mixing ratio and moved it down to 960 millibars, which is where Norman, Oklahoma is, you'd actually get a 61-degree dew point. So what that means is that the 55-degree dew point at Rapid City is the same as a 61-degree dew point at Norman, which means that whenever you're in the higher terrain and you see higher dew points, that's something to watch out for. Something to bear in mind as you're forecasting out there. Now let's do an example profile. So this is a temperature profile that's kind of wild. So this would be basically following the dry adiabatic through looks like about 858, 900 millibars, and then it kind of noses out and moves isothermally until you get to 800, and then cools dry adiabatically uh, as you go aloft, which is not a realistic profile. This would be an unbelievable amount of CAPE, but just for reference here, that's what we have. And then dew point temperature, this would be kind of the same thing. You're not really going to ever see something like this out there, but just for grins and just to show you what this looks like, that's what the dew point temperature would be just to the left. So cooler dew point temperature than your air temperature. If they were the same, then that would be saturated. So generally speaking, your dew point is going to be to the left of your temperature unless it's right on top of it. Now, how to find the LCL? Now, the LCL is the lifting condensation level. So that's basically the level at which the air condenses as it's being lifted. And you can think of that basically like cloud base. So what you do to find the LCL is you start at your surface temperature. In this case, it's very close to 30 degrees, and you follow the dry adiabat upwards. And so you lift dry adiabatically, and at the same time, you start with your surface dew point, which is a little bit above 20C, really, really high moisture, and you follow that up the mixing ratio, a line of constant mixing ratio there, which happens to be co-located with our actual dew point profile here. And where that meets is the lifting condensation level. That's the air or the level at which condensation occurs. Now, I just want you to know that in this case, you may actually see a profile that doesn't, the actual temperature profile doesn't follow that dry adiabat nicely, but you still want to lift dry adiabatically. And the same for the dew point temperature. It doesn't always follow a nice constant mixing ratio, but you do want to follow the constant mixing ratio line when you do find the LCL. By the way, if you do have this situation where you have the temperature profile following the dry adiabat and the dew point temperature following a mixing ratio line, that's known as well mixed. So this would be the case you would, if the atmosphere were particularly well mixed, that's what you would see. The LCL, if you were going to look at that visually, here is a thunderstorm picture I took in 2020, and essentially the LCL would just be cloud base. So where that air first condenses as it's lifted up, that's the lifting condensation level. And it turns out the lower that is, the higher the likelihood of tornadoes. There's a lot that goes into it, but there's been some research on that topic. Okay, so we've talked about this example profile. Now we want to find the LFC. The LFC is the level of free convection. So just because you get to the LCL doesn't mean the air is just going to continue rising. Sometimes it has to deal with some inhibition or a cap that keeps it from rising once condensation occurs. By the way, above the LCL, you do follow this moist adiabat. That's essentially the parcel temperature, and you'll follow that all the way up as you go up the profile here. But where that meets the environmental temperature is the level of free convection. So basically, once it gets above this height, say like right here, that means that your parcel temperature, aka your hot air balloon, is to the right of your environmental temperature, which means that your hot air balloon is hotter than the environment. So it will continue to rise. So that's why it's the level of free convection. So meaning freely moving air in the upward direction. So if you're going to see this in real life, you might think that the LFC is basically the level above the striations or the laminar type of clouds that are between the LCL and say the bubbly cumulus above that. So basically where that goes from laminar to puffy, that's roughly where you see the LFC. Okay. So, and then it turns out that the area that is between the parcel temperature or the moist adiabat here and the environmental temperature, that area in between is known as your convective available potential energy. And that just basically shows you the potential for updrafts within a given thunderstorm environment. So again, your parcel temperature here is to the right of your environmental temperature, meaning that your hot air balloon is warmer than the environment, and so it will continue to rise. So there's potential energy. Okay, so what happens if you increase the temperature aloft here? So this is the temperature line, the environmental temperature. What happens when you increase that? Well, it turns out that you actually decrease that area, so that decreases CAPE. So you decrease the amount of energy you have for updrafts. What happens if you decrease that temperature aloft? You move that red line to the left. Well, you increase CAPE. Now, what happens if you increase your surface temperature, which is like right here? So let's move that off to the right. Well, it does a few things. Number one, increase that area in the Cape because we had a higher, essentially partial temperature than we had previously, a lot more energy, so we have a lot more Cape. We also decreased the convective inhibition, which, by the way, I didn't talk about that. It's the negative area, so that's to the right of the partial temperature and to the left of the environmental temperature. So this would be like the lid or the cap or whatever you would call it. But that would decrease if you increase your surface temperature. But interestingly enough, it would also increase your lifting condensation level, so your cloud base would rise. So that might not be super helpful for developing tornadoes. So something to bear in mind there: as your temperature increases, you're going to get more CAPE, but you're also going to increase your LCL. Now, if you increase dew point, what's going to happen here? So let's see, you got your dew point right here near 20. So you increase it, whoa, you go way off to the right to near 25. You see a huge increase in CAPE, and you do see convective inhibition basically gone. So this is like the Bangladesh soundings that you see with massive CAPE and just a huge cap that gets eroded. 9,000 CAPE, that's kind of that situation. Really not going to happen in real life in most cases, but point being here is that when you increase that dew point, you really massively increase the CAPE despite only maybe raising the dew point by a degree or two. So it is actually really important when you're out there forecasting, trying to forecast tornadoes for storm chasing, that you want to look at surface dew point temperatures and understand that where you do see that increase in moisture, if you see a slog of higher dew point air moving in a direction of your target, that could be really good for increasing CAPE. Okay, equilibrium level. This is the level above the level of free convection at which the parcel temperature equals the temperature of the environment. So basically right here, you can see the parcel temperature in this kind of like dotted line, right? Where that crosses the red line there, that's the equilibrium level. This is essentially the level of the anvil where this all kind of flattens out. So you've seen this with thunderstorms, ordinary thunderstorms as well, where the air goes up and then it hits an invisible lid and then it sort of spreads out. That's where that happens. And sometimes you see overshoots, right? You see, the updraft gets so strong, its momentum carries it above that equilibrium level. That's known as an overshooting top, and it really indicates a very powerful updraft. Now, getting into hodographs. So, a hodograph is a chart used to analyze vertical wind shear. It can be used to quantify bulk shear, storm motion, storm relative wind, streamwise vorticity, and storm relative velocity. So that's a lot. We'll get into that in the second video quite a bit more, but just suffice it to say this particular chart is extremely useful for understanding where tornadoes might form and maybe even how strong they might be. This is this is an example hodograph from May 3rd, 1999, a violent tornado outbreak in central Oklahoma, showing a pretty familiar shape for hodographs. This is known as sickle-shaped hodograph, and basically what this corresponds to is a pretty bad day. If you see something like this co-located with CAPE, which was the case on May 3rd, then you stand the risk of tornadoes. All right, how to construct a hodograph. These are constructed on a polar coordinate chart. So that means that the radials are tied to wind direction. So if you can imagine, this is like north, east, south, and west. And the circles are tied to wind magnitude. So you start at the center, and as you move out, 10, 20, so 10 knots, 20 knots, 30 knots, 40 knots, and so on. So let's construct an example hodograph. So in this case, you see a wind profile that's color coded for its height. So the surface wind is southeast at 15 knots. 1 kilometer is southwest at 40 knots. 3 kilometers is west southwest at 45 knots. 5 kilometers is westerly at 55 knots. And finally, 6 kilometers is west northwesterly at 65 knots. So, how do you plot this on the hodograph? Well, first you place your wind vector at the origin, then you mark the tip of the wind vector, and then you repeat at each level. And once you've done that, you connect all the vector tips. So this is how this would look. So the surface wind, you start at the center and you plot it in the direction of the wind and as far as the wind magnitude will take you. In this case, 15 knots. So you go basically one of these circles plus a half out, and then 1 kilometer is from the southwest, so you plot it in this direction. It's a little longer, right? Because the vector corresponds, the length of the vector corresponds to the magnitude of the wind. And 3 kilometers is from the southwest, so it points in that direction. And then you see so on 5 kilometers and 6 kilometers. You get the picture. And then you draw vectors between the tips of these vectors. So there's a tip right here, 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 and so on. So you draw a line from here to here. Do that here. We'll color it red to represent the level at which it's at. 1 kilometer to 3 kilometer, 3 to 5, and 5 to 6. Okay. Notice that the hodograph trace, which is right along here, this is the hodograph itself, is the difference of wind between two levels. You know what this difference is called? That's right. It's vertical wind shear, vertical wind shear. So basically, the hodograph is a visual representation of vertical wind shear. And then we're going to look at storm motion. So storm motion, um, there was a paper by Matt Bunkers in 2000 that describes a method for finding storm motion for right moving and left moving supercells. So the technique is here on the left. You first find the average wind, and then you draw the 1/2 to 5.5 kilometer shear vector, and then you draw a line orthogonal to that, passing through the average wind, and then plot motion 15 knots to the left and right of that intersection. So we'll go through that exercise here. So the first step is to plot the average wind, which it's a little bit of a guess here, but roughly here is what I'd put. So maybe say it looks like 35 knots east northeast is the average wind. Okay, and the next step is to draw the 1/2 to 5.5 kilometer shear vector. So, half kilometer is probably roughly here. 5.5 is roughly here, so you can draw it from here to here. That little green line represents that shear vector. And then you want to draw a line that's orthogonal to this green line that does pass through that average wind. And then where you see that intersection, you plot 15 knots left and right of that. So this will be the direction and speed of your left mover, and this will be the direction and speed of your right mover. So for the right mover, it looks like it's moving east-southeast at roughly 25 knots, let's say. And the left mover in this case is moving to the east, northeast, almost northeast at, it looks like 10, 20, 30, 45 knots. So quite a bit fast moving. So anyway, that's how you find the storm motion for the left and right movers. And I want to end by saying that observations are key. Now, high-res reflectivity and updraft helicity forecasts are very useful for confirming your forecast mental model, but they should be no replacement for a deep and thorough analysis of the actual weather. And we'll get into how to do that in the next video, but these weather charts will be very, very helpful. Knowing how to interpret them will be very helpful for learning how to forecast for tornadoes. So with that, well, thank you for your attention. And if you thought this video was quality and something that helped you, if you don't mind liking and subscribing, that would be very much appreciated by me. And I will let you know when that next video is released. Thank you very much.